In this module, we want to talk about the processing of glasses. But first, we want to remind you of some definitions. So remember that a glass is just an amorphous silicate. Sometimes it's combined with other oxides. And we're going to introduce a new definition called a glass ceramic. And it's actually a fine-grained polycrystalline form that occurs by heat treating existing glass until it crystallizes. So if we were to look at a cooling transformation curve, hopefully this reminds you a lot of the continuous cooling transformation curves that we saw for metal transformations. Um, we're looking at time on the x-axis and temperature on the y-axis. And the red line represents a beginning of a crystallization transformation, and the blue line represents the finishing of that transformation. So a lot like the austenite to perlite start-finish transformation. So if we have a cooling curve that is shown by this dashed line, that's the minimum cooling rate to get 100% glass part. If we cool at a rate less than that, then we're going to end up cooling through at least some of this transformation region, and we'll end up with some amount of crystalline silicate. So that's how we would achieve a full glass ceramic there. Glass ceramics are used really for their high strength, their low CTE, coefficient thermal expansion, and they can be useful at high temperatures. And they're commonly used in ovenware like pyroceram and Corningware. I'm not going to talk too much more about them because we can form them from existing glasses, and so it's most important about how we form those glasses to start with. We can heat treat them afterwards if we would like to form a glass ceramic. Okay, a couple points about glass properties. So, like polymers, glasses have a glass transition temperature as well. So remember, we looked at specific volume versus temperature, and that's how we actually identified whether something had a glass transformation temperature. So if we were cooling down from a disordered liquid, something that crystallizes would show a jump as it crystallized, and then it would decrease in its specific volume from there. Something that doesn't crystallize, it continues cooling, it becomes a supercooled liquid, and then at the glass transition temperature, it changes its slope, but it doesn't have a jump change in its specific volume. So what that really means is that we sort of have this continuous a continuous property change from liquid into the solid phase, and so we need a way to talk about where we are along that transition. And so what we use viscosity, and we denote that as eta. And all viscosity does is it relates shear stress to the velocity gradient dV dy. And so that's how we use to define various regions of glass behavior. So what we're looking at on this side is if a piece of glass is put under, in this case, a simple shear. If it's flowing, there'll be some velocity associated with putting a force on this glass, and a velocity in the opposite direction associated with putting the shear in the opposite direction there. That's going to give us a velocity gradient, and the relationship between the shear stress and the velocity gradient is defined as the viscosity. Couple things to note about viscosity. Viscosity is going to decrease with increasing temperature. I think that's fairly intuitive. If you try to start your car and it's too cold, the viscosity of the oil is too high, so you need to heat the oil up so that its viscosity decreases so that it can flow better. And viscosity is also affected by the composition of the glass, and we've mentioned some of these before. So remember, we talked about fused silica, which was basically pure silicon dioxide, 99.5%. We talked about soda lime glass, which was on the sort of lower end of silicon dioxide content at 70%. It was combined with Na2O, which is soda, and CaO, which is lime. And then we're going to also talk a little bit about borosilicate glass, which is 81% silicon dioxide, and then boron oxide as well. So So those are kind of three things or three different compositions to keep in mind as we jump to this next slide, which talks about the viscosity, temperature, behavior of glasses. So this yellow curve here is soda lime glass, green is borosilicate, and the red curve is fused silica, so basically pure silicon dioxide. And so what you can see is that for any given viscosity, let's say 10 to the 8th Pascal seconds, uh, the temperature at which that occurs for fused silica is 1500 degrees, whereas for soda lime glass, it's less than 700 degrees. So we define the features of the glass. There's several that we want to be familiar with. The first is the strain point, and that's the temperature formally when the viscosity is 3 times 10 to the 13 Pascal seconds. And so we're showing you that here on this line. Um, it's typically below the glass transition temperature of the material, so it is the point at which the glass is fully solid. It's going to fracture before it plastically strains. So if you put a load on it, it's going to crack. And what you can see is that, let's take the strain point. There's fused silica. Strain point is 1100 degrees. Down at the soda lime glass, we're less than 500 degrees C. Next processing point that's important is the annealing point. And it's defined as 10 to the 12 Pascal seconds. And it's the temperature that when you apply that, the residual stresses are typically going to be removed within about 15 minutes. A third point is what's called the softening point, and it's the temperature defined when the viscosity is 4 times 10 to the 6 Pascal seconds, and it's taken to be about the maximum handling temperature that you can have with the material with no deformation. So let's just look at that quickly. If we're looking at soda lime glass, and this is our softening point looks to be about 700 degrees C. If you go above that temperature, then now the viscosity drops even further, and now you're going to start having the shape change of the glass as you handle it. Another important point is the working point, and it's defined as the temperature when the viscosity is 10 to the 3 Pascal seconds, and at that point the glass deforms very easily. And then finally, the melting point is actually defined as when the viscosity is 10 Pascal seconds, and that just means that the glass is essentially behaving like a liquid. But what I want you to see from this curve is that really we have a continuous transition from solid to liquid, and so we define these 5 points. I don't want to say artificially, but they're defined by convention such that we can identify about how the glass is behaving mechanically at those times. Feature also from this graph that you need to be familiar with is that there's a working range where most of our processing is going to be occurring, and it exists between the working point and the softening point. And then finally, as you can see from the curve, these points are all composition dependent. So if we have a different composition of glass, we were going to expect a different value in any of these 5 points. Okay, so now let's talk just briefly about 5 different processing techniques that we use to create glass products. The first we want to talk about is pressing, and all that is exactly like it sounds. We're going to apply pressure on the glass that's heated up against some graphite-coated cast iron mold, and it's going to adopt the shape of the mold. And this is going to be used typically in thick-walled pieces like plates or dishes. So what you're looking at here is an example of that. We take what's called a gob of hot glass. We put it into a mold. Once it's in the mold, we then press it, and it adopts the shape of the mold. Very simple. If you've a lot of sort of at carnivals or amusement parks or whatever, they'll have glass blowers. That's another method of forming. In this case, all it's using is compressed air to push air into what's called a parison, and we formed one up here just by example, and it pushes the glass against the mold. So if we form this parison here it is now suspended. We apply compressed air into it, and it basically blows the glass, pushes it against the mold, and adopts the shape of the mold. So those are two of the five processing techniques for glass. The third and fourth are actually similar, drawing and fiber forming. All drawing is we're pulling molten glass through a die. So here's our molten glass. We pull it through a die. We can maybe run it through a roller or something like that, a little heat treatment, but we're basically just cooling it as it gets down, and then we have some long piece of glass with constant cross section. So if we wanted glass rods, uh, glass tubes, those kinds of things, that could be done with the drawing process. Even though we talk about fiber forming as a separate process, in reality, it's essentially the same as the drawing process. So in this case, you have your molten glass, and they are drawn through an array of heated orifices, and as they come out, they're cooled, and then they basically go through a series of rollers and are eventually coiled up on a collection spool. So that's how we get sort of continuous um, glass fibers like we might use to make glass fiber reinforced composites. Okay, the final forming process that's important to glasses is sheets. So how do we make things like windows? And sheet forming is basically a form of continuous casting. In this case, we put the glass in, heat it up, get it molten, and then it floats on a bed of liquid tin. And the reason that this is an important process is that it gives us sheets that are perfectly flat with uniform thickness because of the surface tension um, that exists as it passes through surface tension in the glass. So this is how sheet glass comes about today. I think in the olden days we used other techniques like drawing and pressing, but in this case this is how it's done currently. Okay, that's all I want to say about the forming processes for glass. I want to talk really briefly about heat treating glasses. So we didn't cover the mechanical behavior of ceramics or glasses. That will come in the next class. But but when we process glasses and we have to cool them off, we can end up with internal stresses caused by uneven cooling of the glasses, and that happens all the time. And it doesn't just happen in glasses; it also happens in metals. But it's particularly problematic in glasses because, as you know, hopefully from experience, glasses are brittle. And so thermal stresses can lead to thermal shock, which causes fracture in brittle materials. So my example of this is I remember when my grandpa used to take me to school, or at least to the bus. It was a really cold morning, and he was driving an old '79 Lincoln Town Car, and he didn't want to scrape the windows, so he got a hot pitcher of water and poured it on the windshield, and the thing shattered. And it shattered because of thermal stresses that were existing now with the rapid heating of one side and then the cooling of a very cold other side of the windshield, and it just shattered the windshield. So we don't want thermal stresses in general unless we're controlling them carefully, and that leads us to this next heat treatment process, which is called tempering. And all that is is putting the surface of the glass into compression. And the reason we do that is because if we have compressive stresses at the surface and we put a crack in it, then those stresses are going to serve to actually close the crack instead of open the crack. So it helps us to be a little bit more damage tolerant. Um, so how this works is that before cooling, we have some hot part. Initially, when we cool, the surface will cool faster than the interior. We know that. So it forms a solid. But as this middle portion is plastic, as it cools, it wants to contract, and as it contracts, it puts the surface in compression and actually the interior part in tension. And so we end up with a stress profile through the thickness that looks something like this, where these are the surfaces in compression, and the stresses rise up to a tensile stress at the midpoint and then back to compression at the surface. And what that does is it suppresses a crack growth were that crack to form. Again, we haven't talked extensively about it, but in general with glasses, the dominant mode of failure is the propagation of surface cracks. So tempering alleviates that. And in fact, if you do any building of houses or anything like that, as I did recently, at least a few years ago, anytime you have, let's say, windows or something that's going to be by a door or something like that, that window has to be tempered because it's going to give additional strength against fracture if someone were to, let's say, trip and hit the window. So anyway, that's sort of the summary of glass processing and heat treating, and then we'll move on to other forms of ceramic processing in the next lectures.